Welcome to AI Paper Podcasts. This is where we dive into the latest AI and tech papers to pull out the key insights for you.
Yep, breaking down the research so you can stay updated.
Today, we're looking at a really interesting one, AudioX, Diffusion Transformer for anything to audio generation. So if you're an AI researcher, ML engineer, anyone needing to keep up, this deep dive is definitely for you.
Our goal is basically to make this stuff digestible, cover the essentials, and maybe have a bit of fun with it.
All right, so let's do a quick, 1-minute overview for anyone short on time. What's the core story with AudioX?
Okay, so AudioX is this new unified model. It uses a diffusion transformer, and the big thing is it generates both general audio and music.
Unified is key there, and the inputs.
That's the anything to audio part. It could take text, video, images, even existing music or audio.
Wow, okay. Individually or mixed together?
Either, or combined. Super flexible. And a really key innovation is this multi-modal masked training strategy they developed. Helps it learn across different input types much better.
Okay, masked training? And they needed data for this, right?
Oh, yeah. They actually put together two new big data sets, VGG sound caps and V2M caps. Huge contribution there.
And performance, how does this stack up?
That's the impressive bit. Their tests show it matches, sometimes even beats, the specialized state-of-the-art models across a whole range of tasks. Really shows its versatility.
Okay, great summary. So in this deep dive, we're going to unpack how they actually built this anything to audio thing and why it's, well, a pretty big deal for the AI community.
Exactly. Let's get into it.
So you mentioned unified audio generation. What were the roadblocks before? Why was this specific goal, such a challenge?
Well, yeah, it's a good place to start. The whole audio generation field was pretty fragmented. You had models that were great at, say, sound effects.
Right.
Or maybe generating music. But getting one model to do both well, that was rare. And usually, they were limited in what kind of input they could take. Like text to audio models were getting good, maybe some video to audio.
Of not mixing and matching.
Exactly. Combining different types of inputs, like using both text and video to guide the audio generation, that was a real hurdle. Very inflexible, generally.
So it felt like a collection of specialists, rather than one really versatile tool.
Precisely. And that limits how useful these things are in the real world. Think about making videos for social media or films, games.
Yeah, the audio needs are diverse.
Totally. You need all sorts of sounds and music. Doing that automatically with high quality is a huge need. Manual production is just so slow and needs real expertise.
Classic bottleneck situation. And the paper mentioned data issues too. That seems to come up a lot in AI.
Absolutely. A major stumbling block was just not having the right kind of training data. We needed high quality data that linked multiple types of input to audio.
Not just text to audio or video to audio pairs.
Right. Most data sets were just single pairs. Finding good data that, say, combines text, video, and audio descriptions all together, very scarce. And that makes it super hard to train a model that can truly understand how all these different signals relate to the sound.
Okay, so that lack of multimodal data was a key problem AudioX had to tackle.
Definitely. It was a big part of their work.
So along comes AudioX. How does it actually address these limitations? How does it become this anything to audio framework?
Well, fundamentally, it's designed as this single unified system. It can take text, video, image inputs, even existing audio, and use those to generate either general sounds or music. Figure 1A in the paper gives a really good visual of this. You can feed it, a text prompt.
Like waves crashing on a beach.
Yeah, or a video clip, or maybe an image, or even a bit of music you wanted to continue a riff on, or, like we said, combinations of these things.
That flexibility sounds incredibly powerful. And it's not just about the inputs. The model itself is trained broadly.
Exactly right. They trained it on a really large and diverse data set. It covers tons of different audio types, everyday sounds, different environments, lots of music genres.
So it's not just specialized in one little corner of the audio world?
No, the broad training helps it generate a much wider range of sounds compared to models trained on narrower data sets.
And the paper listed a bunch of tasks it can handle. Could you remind us of the key ones again?
Sure. So the basics like text to audio and video to audio, obviously.
Right.
But also more complex things like text-guided audio inpainting.
Okay, what's that exactly?
That's where you have some existing audio, maybe there's a gap or something you want to change, and you use a text prompt to tell the model what sound to fill in or replace it with.
Ah, like add footsteps here or something.
Sort of, yeah. Or replacing a sound. And also text-guided music completion, continuing a piece of music based on text instructions.
Interesting.
And because it can combine inputs, you can do things like generate audio based on both a video scene and a text description telling it specifics about the sound.
Okay, that multi-input conditioning seems really useful. So it covers the anything and the audio flexibility. Let's dig into the tech now.
Yeah.
What are the core innovations inside AudioX that make this work?
Yeah, there are two main things to focus on. First is the architecture itself. They use a diffusion transformer, or DIT.
Okay, transformer architecture. We see that everywhere in AI now. Why here?
Well, transformers have proven really effective for multimodal tasks generally, right? Like understanding how text relates to images. They're good at aligning information from different sources.
Makes sense. So applying that to audio with various conditions like text or video, but why a diffusion transformer specifically? What's the diffusion part add?
Good question. Diffusion models have really become, well, state of the art for generating really high quality, high fidelity signals, especially audio and images.
How do they work in simple terms?
Basically imagine starting with clean audio. The model learns to gradually add noise until it's just static. Then crucially, it learns the reverse process, how to start from noise and carefully remove it step by step to reconstruct, or in this case, generate clean, complex audio.
The denoising process.
Exactly. And compared to some other methods like predicting the next audio sample, diffusion tends to produce audio that sounds much richer, more detailed, better fidelity.
Which you definitely want for realistic sounds or nuanced music. Okay, so the DIT handles the multimodal inputs and ensures high-quality output. What was the other key innovation?
The other really crucial piece is their multimodal mask training strategy. This is how they really push the model to learn the connections between inputs.
Masked training, like hiding parts of the input.
Yeah, pretty much.
Yeah.
During training, they deliberately hide or mask portions of the different inputs. So for video, they might hide some patches of the image frames.
Okay.
For text, they might mask out certain words or tokens. And for audio, they mask segments of the actual audio waveform itself. Figure 3 in the paper shows this visually.
So it's like playing hide and seek with the data across all modalities simultaneously. What's the goal there?
The goal is to force the model to build really robust, unified internal representations. By masking parts, you make the learning harder. It can't just rely on the video information if parts are missing. It has to look at the text or the available audio to figure out what should be in the masked video parts, and vice versa.
I see. So if part of the video showing a car driving by is masked, the text car passes or the audio of an engine might help it fill in the blanks.
Precisely. It forces this deep learning of the relationships between modalities. The paper makes a point of contrasting this with older feature masking techniques.
Right. They mentioned input masking versus feature masking. What's the difference and why is their approach better?
So feature masking usually happens after the input has already been processed a bit, like masking parts of the internal feature vectors. The risk there is information leakage.
Leakage.
Yeah, the model might have already sort of seen the whole input before the masking happens, so it might indirectly know what's being hidden. Input masking, on the other hand, removes parts of the raw input signal right at the start.
Like tearing out the page before reading the book versus trying to ignore a smudged word after you've read the sentence.
That's a great analogy, actually. Input masking is stricter. It really forces the model to learn those cross-modal connections from scratch, leading to more robust generation.
Very clear. Okay, so DIT architecture and this multimodal input masking strategy are the core technical pillars. But you also mentioned the datasets were critical.
Absolutely. You could have the best architecture, but without good data.
Yeah.
And they recognized the existing multimodal audio datasets just weren't quite cutting it for what they wanted to do.
So they made their own.
They did. Two big ones. VG sound caps and V2M caps. This was a major effort.
Let's break those down. First, VG sound caps. What's in that?
So VG sound caps has about 190,000 audio captions. They started with the existing VGG sound dataset, which is basically lots of video clips with associated sounds.
Okay.
And they generated new detailed textual captions describing the audio in those clips.
How'd they generate those captions? Manually.
No, that would take forever. They used another powerful model called Quenin 2 Audio. They took the existing keywords from VGG sound and other similar datasets like audio set strong, greatest hits, AVVP, and used those keywords to prompt Quen 2 Audio.
Prompting a model to describe the sound.
Exactly. Prompting it to write a coherent caption for each 10-second clip. Figure 2 shows the kind of prompts they used.
Clever way to leverage existing resources and models. What about the second one, V2M Caps?
V2M Caps is even bigger, about 6 million music captions. This one is derived from the V2M dataset, which pairs videos with music tracks.
So focused on music this time.
Yep. Again, they use Qwen2 audio, but the prompts were designed to get descriptions of the music itself, things like the genre, the instruments used, the mood, the tempo, even BPM sometimes.
So really capturing the musical essence in text form. Figure 2 probably shows those prompts too.
It does, yeah. Tailored specifically for music description. And the scale is huge, like you said, around 260K audio captions total, and a whopping 5.7 million music captions for those 10-second clips.
That's massive. And they're planning to release these.
That's the plan. They mentioned making them public, which is fantastic for the whole research community. It really helps push the field forward when people share resources like this.
Totally agree. Okay, great architecture, clever training, new data sets. Now, the bottom line, how well does AudioX actually work? They ran a lot of experiments, right?
Oh yeah, extensive evaluations. They used both objective numerical metrics and also subjective tests, with human listeners rating the quality.
And they compared it against other top models.
Exactly, against the leading specialized models for each specific task that AudioX can handle.
And the overall takeaway was pretty positive.
Very positive. Across most metrics, for most tasks, AudioX either matched or actually beat the specialized state-of-the-art models.
Let's get into some specifics. What about general audio generation, like text to audio?
Okay, looking at Table 1 in the paper. For text to audio on standard benchmarks like Audio Caps and VGG Sound, AudioX achieved state-of-the-art results. They noted the improvement on VGG Sound was particularly strong, likely thanks to those new captions they generated for it.
Ah, the V2M Caps data paying off.
Seems like it. Then for video to audio, again on VGG Sound, and also on AVVP, which was kind of an out-of-domain test.
Meaning data it wasn't explicitly trained on?
Right. It performed comparably to the state-of-the-art there, too. Showed good generalization.
Nice.
And when generating audio using both text and video as input, it stacked up well against strong baselines like Foley Crafter and Audio. Showed it could really integrate info from both sources effectively.
That integration piece keeps coming up. How about music generation? Same table?
Yep, lower part of Table 1. Text to music on music apps, and also video to music, or text plus video to music, on their V2M dataset state-of-the-art performance again. Really solid results for music.
Okay, impressive on the main generation task. Did they test other things like manipulating existing audio? You mentioned Inpainting.
They did. Table 2 covers audio Inpainting results on Audio Caps and AVVP. AudioX outperformed the baselines there too. They also tried different ways to guide the Inpainting. Just filling the gap, using video as a guide, or using both text and video.
And what worked best?
Interestingly, both text and video helps guide it. Sometimes text was even slightly better. But the absolute best results came when using both text and video together. Again, that multimodal synergy.
Makes sense. What about music completion? Finishing a musical phrase?
Right, Table 3 looks at that on their V2M bench. The task is, you give it the start of a music clip and it continues it.
Yeah.
What they found was really cool. Performance got consistently better as they added more input modalities. So just music input was okay, adding text guidance improved it, adding video improved it further, and using all three, music start, text, and video, gave the best completion results.
Wow, that really demonstrates that intermodal learning capability, doesn't it?
It really does. Strong evidence for it.
And they even tried image to audio. That sounds wild. Was it trained for that?
Not specifically, no. That's what's wild. Table 4 shows zero-shot results. They just gave it images and asked for corresponding audio. And it did remarkably well, compared favorably to models designed for image to audio like Seeing Hearing or M2Wave. Even better than just using an image captioner plus a text to audio model.
That's pretty mind-blowing. Suggests a really deep, generalized understanding of sensory information. Imagine the creative possibilities there.
It's really intriguing. And finally, they didn't just rely on metrics. They got humans involved.
Right, the user study. What did people think of the audio?
Figure 4 has those results. 10 professional users listened and rated the quality and relevance. For most tasks, text to audio, text to music, video to audio, video to music, AudioX, came out on top in the subjective scores too. Both overall quality, OVL, and relevance, RDL.
So it doesn't just score well on paper, it actually sounds good and relevant to human ears.
Exactly, that's crucial validation.
Okay, before we wrap up, they usually include ablation studies in these papers, right? To test specific design choices.
Yes, absolutely. Super useful for understanding why things work. They looked at the mask ratio first, how much of the input to hide during that mask training.
Did they find optimal amounts?
They did. Figure 5 shows this. For text, masking about 20%, a ratio of 0.2, seemed best. For video and audio, masking more about 60%, a ratio of 0.6 worked better.
Interesting that video needed more masking.
Yeah, and they theorized it's because video often have a lot of redundancy between frames. Masking more forces the model to really latch on to the important changes in information, rather than just relying on static background stuff. They saw the biggest performance jump from masking video.
Makes sense. What else did they ablate?
They directly compared their input masking strategy against doing no masking, or doing that feature masking we talked about earlier.
Did input masking win out?
It did. Table A3 in the appendix shows input masking boosted performance, while feature masking actually made it slightly worse. Really reinforces their choice and the idea of avoiding that information leakage.
Okay, solidifies that design choice. Anything else?
One last important one. They compared their single, unified AudioX model against models trained only for one specific task, like a model trained just for text-to-audio versus the unified AudioX doing text-to-audio.
Right. Does the jack of all trades suffer compared to the master of one?
Well, Figure 6 shows the results. For these intramodal tasks, the unified AudioX often performed just as well, or even slightly better than the specialized models.
Really? So no penalty for being unified, maybe even a benefit.
Seems that way. The unified training might actually help it learn more robust features that benefit individual tasks. And for intermodal stuff like music generation, they showed again that adding more input types, text, video, music, consistently improved results. The unified approach really shines there.
That's a powerful finding. It really ties the whole story together. The unified approach isn't a compromise, it's potentially an advantage.
Exactly.
Okay, let's try and summarize this deep dive into AudioX then.
Sure. I mean, AudioX clearly represents a pretty big step forward for unified audio and music generation. It skillfully combines that diffusion transformer architecture with this clever multimodal masked training, allowing it to effectively handle this wide range of inputs: text, video, images, audio itself. And crucially, the new datasets they built, V2M Caps and V2M Caps, were likely key to its success and are a great contribution themselves.
Definitely. And the results speak for themselves. Its versatility is impressive. It can tackle so many different audio tasks and often performs as well as, or better than, models built just for one specific thing.
It really pushes towards that goal of having truly general-purpose AI for audio creation, synthesizing sound from almost anything.
Okay, so here's a final thought for everyone listening. With a technology like AudioX emerging, one that can generate sound from nearly any kind of input, how might that change things? How could it revolutionize workflows in content creation, game development, filmmaking?
Yeah, or even open up completely new types of art or interactive experiences we haven't even thought of yet.
Exactly. It's worth considering the ripple effects. What could you do with a tool like this? Think about the implications for your own work, your own research.
And remember, the authors mentioned the code, and those datasets will be available. So definitely worth keeping an eye out and maybe exploring it yourself when they release it.
Absolutely. Well, that brings us to the end of this deep dive on AudioX. Thanks so much for tuning in to AI Paper Podcasts.
Hope you found it useful.
We'll catch you next time with another look at cutting-edge AI research.